and Assalamualaikum. My name is Aimmi Najihah Abdul Wahab and my supervisor is Dr. Fazila Zawawi. So today I'm going to present about my final year project entitled CFD Analysis of Centrifugal Pump Impeller for Oil and Gas Platform. So this is the outline of my presentation today. I will start from the introduction, literature review, methodology, results and discussion, and last but not least is the conclusion. The main function of the centrifugal pump is to increase the pressure of the fluid, and its main part is impeller. This part makes the most contact with the medium flow and will compress it in order to transfer it to other area or equipment for further process. It is essential to manufacture pumps at lower cost with minimum time, consuming less power with high efficiency. Plus, it is very important and widely used in Malaysia. Various kinds of centrifugal pumps are widely employed. For example, firefighting pump, hot water circulating pump, and sanitary water pump. So now let's move on to the case study of this project. In this research, the location of the data collected is at one of the oil and gas platforms in offshore Terengganu, which has the highest number of centrifugal pump malfunctions. This is the major problem to the company, as the centrifugal pump is very expensive and having pumps in downtime could lead to financial deficiency. So these are the problem statement for this study, and the issues are cavitation, excess vibration, excess noise and heat, leakage, components and mechanical seal failure, which is caused by rattling noise, high level of vibration, loss of energy in the fluid, and as the consequences, it creates small holes on impeller, pressure drop, head pressure decrease, and low efficiency. So as a solution for this problem, we will need to design a new centrifugal pump impeller and do maintenance work. The goal of this study is to optimize the design of the centrifugal pump impeller in order to increase the efficiency and enhance the pump performance. And the objectives are to develop a validated numerical model of an optimized centrifugal pump impeller and to perform parametric studies on the centrifugal pump impeller in terms of geometry and operating condition. When carrying out a research, there are variables that could influence the results of the final outcomes. Having those variables scoped down to a decent figure could give better results and greater focus in the research. For this study, the scopes are number of blades, rotational speed, inlet and outlet pressure, and lastly the blade angle of the impeller. First is centrifugal pump, and the title is CFD Simulation of Centrifugal Pump Impeller using NCCFX, and the author is Mohd et al., written in 2014. It stated, centrifugal pump is a type of a turbo machinery which converts mechanical energy to dynamic pressure to enable the lifting of liquid from lower level to higher level due to centrifugal action, and the picture shows the liquid flow through the pump. Next is CFD analysis, and the title is Computational Fluid Dynamics Analysis of a Mixed Flow Pump Impeller, written by Manivanan in 2010. From the results, velocity and pressure in the outlet of the impeller is anticipated. These outlet flow states are used to calculate the efficiency of the impeller. The most appropriate inlet and outlet vane angles are calculated. The CAD models of the mixed flow impeller with optimum inlet and outlet angles are modeled using CAD modeling software. So for parametric study, the title chosen is Parametric Study of a Centrifugal Pump Impeller by Varying the Outlet Blade Angle, and the author is Basharuddin et al. In 2008. It stated that analyze the performance of pump by varying the outlet blade angles by keeping the same outlet diameter. The numerical simulation of 3D incompressible Navier-Stokes equation was carried out with a commercial CFD finite volume code at nominal capacity when the outlet blade angle was increased from 20% to 50%. So in order to achieve objective 1, we will start by modeling a centrifugal pump impeller with CAD software, and the one that I'm using is SolidWorks and ANSYS Blackjan, and then ANSYS pre-processing. Next, impeller geometry and flow modeling. We also need to set the boundary conditions, and after that is the meshing process, solver setup, and lastly is ANSYS post-processing. Pump specification need to be studied before the impeller can be designed, because the performance of the radial flow pump is hugely affected by the geometry of the pump. So the figure shows the impeller design. The first step to design each part of the impeller is the most crucial one. Every step and calculation must be determined and carefully examined. This is because the understanding and correct procedure to construct the impeller are the reference for further design by using CAD. So these are the geometry of the pump. The impeller is considered as a rotor of the centrifugal pump, while the volute is considered as the stationary part. The impeller blade models were matched by the use of ANSYS turbo grid. The number of nodes and elements is shown in the table. The figure shows the volute mesh. Abstracted grids used were concentrated near the cutwater areas. The number of nodes and elements is shown in the table. The following boundary conditions are used in the pump. At the inlet, the mass flow rate is equal to 0.032 m3 per second, and at the outlet of the pump, static pressure is equal to 0 atm. No slip conditions are assumed at the wall of the blades, hub and shroud of the pump. The interface between the rotor and stationary part of the model is staged. So in order to achieve objective 2, I was supposed to also manipulate the number of blades earlier, but as the limitation of time, I only managed to manipulate these two variables, which are the blade angle and the rotation speed, and the responding variables are the static head, inlet and outlet power, and effect of efficiency can be seen in the plotted graph. So this is the DOE for case 1, where I only manipulate the rotational speed. The first one is 1150 rpm, the second one is 1750 rpm, and the last one is 2500 rpm. The input and output powers were calculated in order to obtain the impeller efficiency and static head. The value of flow rate, torque, density and gravitational acceleration is set to be constant. So this one is for case 2, where I have 9 models and I manipulate the value of rotational speed and outlet angle. In this, there are 3 different rotational speed that I have used, which are 2500 rpm, 2500 rpm, and lastly is 2600 rpm. And there are also 3 different outlet angle, which are 24 degree, 28 degree and 32 degree. So by using CFD and DOE prediction model, it is easy to predict the performance of different pump and speed up the production. Pressure distribution, and this one is for the type A, which has the 1150 rpm, and the figure shows are the front and the side view. Okay, the simulation results shown at the left side of this figure, where the impeller has a maximum pressure of 740 kilopascal and a minimum pressure of 270 kilopascal. The pressure at the inlet of the impeller is 624 kilopascal, while the outlet of the impeller has a pressure of 740 kilopascal. So this one is for type B, which has 1750 rpm. From the observation of these figures, the impeller has a maximum pressure of 785 kilopascal and a minimum pressure of 310 kilopascal. The pressure at the inlet of the impeller is 543 kilopascal, while at the outlet has a pressure of 785 kilopascal. So the last one is type C, which has 2500 RPM. From the observations, the impeller has a maximum pressure of 1011 kilopascal and a minimum pressure of 406 kilopascal. The pressure at the inlet is 557 kilopascal, while at the outlet is 1011 kilopascal. So these are the formula for impeller power and efficiency calculations, where we have inlet power, outlet power, efficiency, and static head. So this table shows the power at the inlet and outlet of the impeller and the overall efficiency of the impellers. The efficiency of the impeller can be calculated based on both powers. It can be clearly seen here that impeller C has the highest efficiency with 69.39%. The following table shows the static head produced by each of the impeller at various rotation speed. At 2500 RPM, impeller C has the highest static head produced, which is 46.28 meter, followed by impeller B and impeller A. So the first figure shows that as the impeller's rotation speed increases, the efficiency of the impeller increases as well. The highest efficiency is recorded by impeller C with 69.39%, whereas the lowest efficiency is recorded by impeller A with 38.55%. And the next figure shows the relationship of rotation speed with static head. It is clear that as the rotation speed increases, the static head also increases. The analysis result shown was from the NCCFX. The modified parameters for the impeller are the blade angle and rotating speed. Efficiency, total pressure head developed, and shaft power is calculated in the fluent for different models. It can be inferred from the results that the pressure head increases as the rotation speed increases. The efficiency of the impeller decreases as the rotation speed of the rotor increases. Finally, the pressure head will increase as the angle of the outlet blade increases. To make it more clearer, we can see from this graph, as the rotating speed increases, its efficiency will be decreased. This graph shows the relationship of pressure head and impeller rotating speed. It is clear that as the rotating speed increases, the pressure head will also increase. Based on this study, these are the conclusions I have made. The performance of the impeller increases as the rotation speed of the impeller increases. Next, by increasing rotation speed, the efficiency of the impeller will also increase from 92.22% to 94.84% in case 2. And lastly, the pressure head increases as the angle of the outlet blade increases. So we have come to the end, and I think that's all from me. If you have any questions, feel free to ask me during the Q&A in the next session. Thank you. Stay safe and have a nice day.